Question number 14 says a light rod of length 1 meter rotates about an axis perpendicular to its length and passing through its center, as in the figure below. Two particles of masses m equals 4.45 kilograms and m2 is 3 kilograms are connected to the ends of the rod. A. Neglecting the mass of the rod, what is the system's kinetic energy when its angular speed is 2.7 radians per second? And B. Repeat the problem assuming the mass of the rod is to be taken as 1.6 kilograms. So the kinetic energy of a system, centripetal rotational kinetic energy, is 1/2 of the moment of inertia times the angular speed squared. So what we can do is we can break this down to what we have. So KE is going to be equal to 1/2 of the mass times the radius squared times the angular speed squared. And now what we would do normally is we would say that the kinetic energy is 1/2, or we would add up each individual component. So we would say 1/2 times mass 1 times R1 squared times the angular speed plus 1/2 mass 2 times R2 or R2 squared times the angular speed, and we would add up all of our masses. We only have two masses, and the great thing is they both have the same radius. So there's a whole bunch of things that are the same here. The angular speed's the same, the radius is the same, and this 1/2 constant is the same. So what we can do is we can factor everything out except for the masses. So we'll factor it all out, and we'll say that our kinetic energy is equal to 1/2 of the radius squared times the angular speed times mass 1 plus mass 2. And we can get this easy result because they are the same radius apart. So we can plug in our numbers. The radius, it says that the rod is 1 meter, so the radius is going to be 0.5. So we've got KE equals 1/2 times 1/2 squared. So we could actually just combine that to just be 1/2 cubed times the angular speed, which angular speed, it says in the problem, is 2.7 radians per second, and we're going to square that. We're going to times that by mass 1 plus mass 2, 4.45 plus 3. So 0.5 cubed is 0.125, and 2.7 squared is 7.29, and then this term turns into 7.45. So we just multiply that all out and we get the kinetic energy, assuming that the rod isn't taken into account. So we get that the kinetic energy of these two masses is going to be 6.788. And then it asks in part B, repeat the problem assuming the mass of the rod is to be taken as 1.6 kilograms. So what I want to do is I want to remind you that the formula for I, for the moment of inertia, with a rod like this, is going to be 1/12 of m times the length squared. And we're going to be able to keep this number and just add it to whatever kinetic energy is produced from the rod. So we would take the mass of the rod, which is, actually we'll just set it up like this. So the KE of the rod is equal to 1/2 times, and this is, so it's 1/2 of I omega squared, so we're going to break out I to its components, times 1/12 times the mass, it said, was 1.6 kilograms, so this times 1.6 kilograms, times the length, which we said was 1, the length squared, 1 squared is going to, that term's going to cancel out. Then we're going to times it by the angular speed squared, which is still going to be 2.7 squared. So you just plug that into your calculator, and you're going to get the kinetic energy of the rod is 0.486. Just add that to your 6.788, and you get that the total kinetic energy is roughly 7.27481 if you carry all your decimals.